tardes, muchas gracias por venir. Es un honor para mí presentarles hoy a nuestro querido colega, profesor Martín Madrid, que nos va a hablar de Esperanza condicional. Adelante, Martín.
Gracias. Good. We go in English as always. So, Esperanza condicional with a well-specified problem. And we see many things, including Esperanza condicional. So, joint distribution of x and y. See? Which is given by this. E minus x, where on this support. Okay? Everyone minus 2 takes classes with me, so no doubts you understand what it is, no? So this is the joint of two random variables evaluated in 2 points, no? So at first sight, maybe this can look a little bit strange, no? Because you have 2 variables, but only x here, no? So where is the second? So what does this mean? That the density basically depends only on the x, no? So if I have a point x, y1, and a point x, y2, another point x, yn, the x is the same. The density doesn't look at the y, no? So all these guys have the same density, e minus x, no? Yes? So what does it mean? And second thing, this is the support, no? So x can be wherever, but y is between 0 and x, no? Now, to say this thing. So, this guy here is the surface. This is the density, no? So, what is the idea? It depends only on the x, when the x is fixed, no? So here I fix this x to this value, no? Yes, so all the point here have the same x, no? Outside the support, okay, we don't care, y is 0. Here, for those values of x, you see, the density is flat, no? All the same y's for a given level of x, it get the same density, no? Right? So, this is the idea. And if you want to see the domain, I use nothing because you can do these kind of things. You rotate now. And this is exactly a triangle, no? Once you're given an x, y gives between 0 and x, no? Now, let's continue. So, first problem, get the marginal of x. Yes? How do we do this?
We integrate.
Yes, you integrate the density with respect to I don't care, no? dy. And now y goes from where to where?
From the support of
Yes, once I fix x, y goes from 0 to x, no? Move it in. So from 0 to x of who? E minus x, no? So what do you get? E minus x, and then you have y, 0, x, no? So this gives you x, e minus x. See? Where x is always well defined, no? X greater than 0. See? So what is the idea behind this, no? Okay, mnemonic thing is I integrate the joint with respect to the other variable, no? Practically speaking, let's go back to this. If he allows me, no? Here we are. So I want to evaluate the density at a given x, no? So I fix the x and I want to get the density for this value of x, no? What do? You integrate with respect to y along this line. So I integrate with respect to y from 0 to the point x, no? Yes? So what does it mean integrating under this curve from here to here? It means computing the area under the curve on the line from 0 to x, no? So you see this is a rectangle, yes? What is the area? This. Makes total sense, no? The base of this rectangle is x. All these points have the same x, so they have the same value of the density, e minus x. So you see, this is exactly the base and the height of that thing, no? Yes? So what is happening here? Basically, you are accumulating area under the joint in x, no? So you have an x that has this distribution, no? This probability mass function. So what is the distribution of x? So x is what? How can it be Poisson? Continuous. Maybe you want to remember that the gamma, alpha, beta has this density, no? X. Yes. So what would be the case for a gamma 2, 1? 1 to the power of 2, 1. Gamma 2 is 1 factorial, 1, okay? X to the 2 minus 1, e minus x, no? So you see, this is a gamma 2, 1. See? Okay, we have to go to the conditional expectation, so we need to get the conditional density. For doing the conditional density, we also need this guy here. How do we do? Same story, no? Integrate the joint with respect to x, no? And x goes area is infinito. No? So you want the density of y, no? So once you fix y, x goes from the y onwards, no? So y infinity. Yes, so e minus x, dx, right? And here we get minus e minus x, y plus infinity, no? And this is equal to? When you put here, this goes to 0, no? Minus e minus y. See? So, what is the distribution of y? Maybe you want to remember that an exponential with parameter lambda has density, no? So this is an exponential one. Okay? Now I don't remember if I have to do y given x or x given y. So probably I have to do with y given x. Okay, so now next step. Y given x. What is this distribution? No? So you need to get the margin. See? F y given x, x. Right? What is this? How do we do it? Joint, no? Divided by this, no? The joint is e minus x. The margin of x is that gamma thing. See? So, 1 over x. Make sense? So, the conditional distribution y given x, once you are told what is the given x, is simply 1 over x. No? This is also, again, is the conditional of y, so it's about the y. And the y lives from 0 to x. No? So you have something surprising maybe. No matter what is y in this interval, the density is 1 over x. Any idea what does this mean? So it means that y lives in this interval. And in this interval, the density is 1 over the length of the interval. Y given x equal x is what? Is a uniform 0 x, no? Same? Make sense? What is the density of this thing? 1 over the length of the interval, no? You have it, no? Yes? Okay? So if we go back again to this thing, maybe. Here you have it, no? You fix the x, no? And now you want to understand what is the density of the y for this x, no? So once you're fixing the x, you can imagine us cutting the distribution with a plane, no? And looking at the y on that plane, no? Yes? So the result is this. So all the y's that are on this line, where I got the thing, have a distribution that is 1 over x. Yes? So this is the conditional distribution of y given x. You see, x is 1.62 blah blah, no? If you do 1 over, you get this number here, no? And this is the conditional distribution of y given x, no? Okay? So now the idea is, what is then this? So, is the expected value of the conditional distribution. So I have this conditional distribution, the uniform, and I am asked, what is the expected value? Yes? So it can be very simple now, because you know that this is a uniform from 0 to x, so what is the expected value? Let's write a little bit loosely, expected value of the uniform 0x, no? Is the midpoint. X divided by 2. No? If you don't realize that this is a uniform, can you still do it?
Yes.
Yes. Yes, no? You apply the definition, no? Y, fy given x, yx, and you integrate, no? For dy over where the y lives, 0 to x. You have all the ingredients, you see, you will end up at the very same place, no? No need to do it. Okay, and now the big problem is the following. So we need this and nothing else. What is this? Yes. So, what is this is a little bit ambitious to do it in this course. So, let's get the idea, no? You are users of the concept, not doing research on it, no? So the idea is, this is a random variable. And specifically is the random variable that if x happens to be the value x small, yes, if y given x will take determination E of y given that x is x. Okay, so this is a random variable. A random variable has determination, no? And what determination is this guy having? Well, if x happens to be this number, then the determination of this random variable will happen to be this, no? And for our example, this is x divided by 2, no? See? Okay, now let's open up parentheses. X big divided by 2. What is this? Let's put it in this way. This is a shorthand notation, no? For a new random variable, which is the transformation of x when you divide it by 2, no? But that practically works like this is shorthand for this is a shorthand notation for a random variable such that if x happens to be this value, x divided by 2 will have a determination x divided by 2, no? Yes? So when you write this, what do you mean? You mean something that if x happens to be 5, this is 5 divided by 2, no? Usually, no? When you write g of x, what is this? You imagine that if x happens to be 3, the random variable corresponding behind this object would be g of 3, no? Yes? So, you see, this guy is the same determination as here, no? Yes? So you can think of e of y given x as this thing here, no? Yes? So in conclusion, people will have e of y given x is x divided by 2. Yes? And it's really x divided by 2. I think it's equality, not in distribution. Okay? So this is the area. It's a random variable, but it's equivalent to this one, no? Since this is a random variable, it will have a distribution. Which is the distribution? Is the distribution of a gamma divided by 2, no? Which is a gamma 2, 2. Yes? So the determination of this thing here are not uniform. Follow a gamma. So the idea, maybe you have it here, no? I draw an x. This is the conditional distribution for that x, and this is the expected value, this number, no? If I draw the thing again, I sample another x, no? I have another conditional distribution, 1 over the x that happens not to be, and this is the expected value, no? So you see, before it was here, now it is here. I do it a couple of times. You see, this square here changes position because I changed the x that is behind the sample, no? Yes? You can also happen to have the square here, no? But this is very unlikely because this will happen only if x happens to be very far, no? But the marginal of x is a gamma, so it will mostly be in this region, no? Yes? So you understand, it's not really flat. There is a distribution beside it, and it's this one, no? Yes? So let's see one more thing. So we said that y is what? An exponential 1, no? So something that you know already is how much is this? It's the average of the exponential, no? So you know this delta is 1. Yes? Okay, let's see if we can do it in this way. No? This is the law of total expectation that you have seen with me, or you have seen with someone else, but you have to know, no? So what does it mean? You take the average, the expected value of this guy. This is a random variable, so taking the average of a random variable totally makes sense, no? Yes? E, this is x2, no? 1/2 e of x. X is what? A gamma 2/1, no? The expected value of a gamma alpha beta is alpha over beta, no? 2 over 1. So it's 1/2 times 2 k delta. Okay? Okay? Questions? Good. We have time? Good. See? And then we do the same thing, x given y. Yes? So now what is this distribution? See, no? No. F of x given y. What do you have to do? Take the joint, right? And divide by y, no? E minus x, E minus y, because it's the exponential, no? See? What do you have? E minus x minus y. Okay? What is this distribution? So, the density of the conditional of x given y is this one, no? So if I want to answer what is the distribution, I have to understand what is the random variable that has this df, no? See? So here things are not obvious, well, but also not difficult. Now, yesterday we did transformations of random vectors, so you are supposed also to know what are transformations of random variables as in the first partial, no? Imagine that you take zeta that is an exponential 1, yes? And you define a new random variable, w, that is zeta plus y, some constant, okay? What is the distribution of w? Density. You have to use the change of variable theorem, no? So here it goes. The density of where you starting, zeta, no? And here you go with the inverse transform, no? So this is the g, the inverse would be minus y, no? Yes? Here you have the absolute value of the gradient with respect to this, no? 1, so no problem, no? F zeta is the density of the exponential, no? So you get E, the exponential zeta is parameter 1, no? So the minus lambda is not there. X, W minus y. See? So you see you get the same density, no? So practically speaking, this is like taking an exponential with parameter 1 and shifting it by y. Okay? Then things are easy if you have that representation. E of x given y equal y is the expected value of this random variable, no? So it's the expected value of your zeta plus y, no? So 1 plus y. Okay? You can also do it integrating it brute force from this, no? But I don't like integrating and you even less. What is this guy? E of x given y. Is a symbol for a concept. The concept of a random variable that if now y happens to be this random variable will take this value, no? Yes? For the specific example, this is 1 plus 1. Small, no? The conditioning by small, no? On the other hand, what is 1 plus dy? Well, it's taking an exponential and shifting it, no? But this also represents a concept of a random variable that if y happens to be y, this object will take as a determination 1 plus y. Okay? So you see the determination when y happens to be something of this. And of this are the same, no? So you can prove this conditional expectation is 1 plus y. Yes? Okay, so same story here. Same distribution, but seeing in the other side, no? Here you condition for a y, no? This is the marginal of y. And when you look at this marginal, it looks very much like an exponential, no? It is the exponential of parameter 1, no? to look at the expected value of x given that y is y, no? So given that y is y, x lives on the line from y to plus infinity, no? Yes? Yes. And the density of this x condition of y, we have said that is an exponential shifted by what y happens to be. Now you see this thing here, this is much like an exponential, no? But this exponential, it's shifted, no? And this value here of the shift is exactly the one of the y, no? Yes? And then, to finish the analogy, e of x. So x was the gamma to 1 initial, no? So we already know that this should have been 2. But let's do it with the law of the expectation. See? Expected value of this guy here. 1 plus y. See? 1 plus expected value is exponential. 1 equals 2. No? Yes? Let's see this. Which one? Question so far? No. No. So here what we use the trick that you see as a yes.
When we calculate the function of the density of W, we have the function of the density of the sigma with the inverse. That, yeah, and we multiply it by what we have 1.
Because the g minus 1 small w, no? Is this, no? Do the derivative. It's just 1, no?
Okay.
So you should also take the absolute value here.
Okay.
Yes? Okay. So let's say that I have 5 minutes because you started late. Yes? You came late. I will show you one more thing about conditional expectation that I think is nice. Well, let's use this part, okay?
Apaga el proyector.
Por favor, sí. So conditional expectation now for you is just some fancy thing that has little connection with reality, no? But when you come to econometrics, it will become something very important. So also to do a little bit of more generic exercise, let's compute this thing here, okay? So this is the expected value of the y multiplied with a new random variable that is a whatever g of x, no? How do you do this? Is a version of Lotus or Lane, no? Yes? So you integrate what y g of x, no? The thing that you have here, and then the joint. See? The y, the x. X is the same as the example before, no? Plus infinite, and y that goes from 0 to x, no? Yes? Okay, so let's replace the things. Y, g of x, here you have e minus x, dy dx, no? 0 plus infinity. Everything that has an x, I put it on one side, and then I have to integrate with this guy with respect to y, no? Yes, sir? Oh, that's right. Yes? So what do you get here? Y squared divided by 2, 0, x, no? Yes, so this, at the end of the day, is x squared divided by 2, no? Yes? So you have integral in 0 plus infinity of what? Of x squared divided by 2. because you like to complicate things, you write it like this, okay? Yes? So what do? You put the 1/2 x here. You put the g of x, yes? And then e minus x dx. See? Now, what is this? Okay, maybe clearer if I do it like this. What is this? I am see it as lotus overlay again. This is 1/2 e of x g of x, no? Yes, it's the same concept that we used here, but now here in one dimension, no? Yes. And then bring this thing inside. You have this. So you have something very special. What is this? This is the conditional expectation of y given x. So the conditional expectation has a very cool property that always satisfies this relation whatever x is g, or whatever g is. So basically speaking, with the conditional expectation, we have this. E of y, g of x is always equal conditional expectation of y given x, g of x, for every g that you can think of. Okay? Now, without doing big magic, if you bring this to the other side, you get a 0, no? So, if you collect pink on one side, you will get this. For every g, no? Yes, sir? You move this here. You collect the expected value, arrange for the g, you have this, no? Then call this epsilon. Okay? This is a random variable, no? This is a random variable. This is a random variable, differences of random variables and your random variable, no? But I don't want to write a lot, so I write epsilon. So you have this. See? For every g. And now this is the point. So imagine that you are interested in what is the covariance between epsilon and g. Okay? So you can write the covariance as this: epsilon g of x, right, minus. You remember, I'm talking about something that usually you see like this, no? Is this. So minus e of epsilon, e of g of x, no? So this guy is 0 because this is a condition that the conditional expectation satisfies, no? What about things here? This is whatever. It depends on g, no? And also on x. But e of e, you apply the law of the expectation again. You write it in this way. See? Okay? So this is expected value of e. Here I will put what epsilon is given x, no? Okay? And my epsilon is this. See? So you see what happens here? This given x, this expectation, you split it, no? Here you have the given x, here you're conditioning 2 times redundant, you get a 0, no? Yes? And the expected value of a 0 is a 0. Okay, so the covariance between this and g of x is always 0, no matter what is g. So thinking of covariance can be a little bit unfriendly, so the question is, what is the correlation between epsilon and g of x? Correlation is covariance over blah blah, no? If the polarity is 0, you can also say that the correlation is 0 for every G. So this is something meaningful. So this condition here is basically saying that the correlation between an epsilon and a G, or between the epsilon and the G, is always 0, no matter what is G. So now think at a higher level. You have a random variable y, and you have another random variable. You are using this random variable as an approximation of y. Okay? Or you are using this. This is a statistical model that you use to describe y. Yes? So this epsilon is what? Is your approximation error between the conditional expectation and the reality that is y, between what is y and how you approximate it, no? So this error satisfies this thing, which means this. So what does it mean? That the correlation between your approximating error and any g of x is 0. If you would know that the correlation is not 0, it means, for example, that if one variable goes up, the other goes up, or if one goes down, the other goes down, no? So you could exploit the fact that the x is growing to sort of predict that also epsilon will change, no? So if the correlation is non-zero, you have some predictability for the error, no? Yes? And how do you predict it? You can do it in a very simple or very complex way. With that g, that is what you use to predict, no? So this is basically saying that if you use the conditional expectation as an approximation for the y, the error cannot be explained by the x in any form. So you cannot improve this approximation. In any possible way, you can transform the x and you can invent to find a correlation. The correlation simply doesn't exist. So the conditional expectation is the best approximation ever you can do of y when you only have x. Whatever is left over cannot be explained by x in any other form. See? And so if you do econometrics in a principled way, you will have a model for this, and if this is a correct model, you will already know that this model cannot be beaten in these terms. Okay? Y exit. Terminamos.
No sé si alguien quiere preguntarle algo al profesor Martín.
Well, in any case, I have come later from 4 to 5.
Bueno, pues muchas gracias. Los que no se hayan registrado.